Greetings everybody and welcome to part 4 of the Manifold series. Today we're taking a look at differentiability, which is roughly speaking how you can differentiate things on manifolds. So we're going to be putting those maximal atlases we saw in the last video into action in order to define differentiability. But before we take a look at differentiability, we have to take a look at some manifold philosophy, if you want to call it that. So our topological manifolds so far, they're very, very abstract spaces. Sometimes we have objects involving our manifolds, for example, functions on our manifolds or between manifolds and whatsoever. And because our manifolds, they're very abstract still, what we can do, we can take a look at charts, because charts, it's a map of a manifold into Euclidean space, and we understand Euclidean space very well. And what we can do is we can maybe look at those objects or functions in terms of a chart, and we want to describe properties of those functions. The question is, can we describe them in terms of a chart? Is that a good thing to do? So the question is, I'll write it on the blackboard. Can we define properties of functions involving manifolds using charts? And the answer to that question is yes, but you have to be extremely careful. So let's take a look at a rather simple example, and the example I'm going to give is the continuity of a function. So continuity. So when we take a look at manifolds, we might consider 3 specific cases in terms of functions. You might have something called a curve, which is just a map from R into your manifold M here via some map gamma. So this is what we call a curve. You might have a map between manifolds. So this is just a map here, so maybe a map phi. And then finally, you might have a map on your manifold into the real numbers via some map f. And this is usually what we just call a function. So let's pick one of them. Let's say this guy over here to investigate, and we might touch on these other 2 cases later in the video. So we have a curve gamma that's running through our manifold in some way. So you could think of the manifold for this example as being just the room we're living in, so R3 or something like that. You could imagine a curve that's running through the manifold. The question is, can you determine if the curve is continuous or not? Well, because topological manifolds, they're just topological spaces. Of course, you know what it means for a curve to be continuous. You just use the topological definition of continuity, which is pre-images of open subsets are open subsets. But the question is, can you do this using a chart, right? Because the manifold is very abstract. Can we think of this curve in terms of a chart? So what you could do is you could take a look at what the curve R, but then you only map into a small section of your manifold. So this is some chart domain U here. And then you can consider the chart's map X, which goes down into some, R to the dim M here. Or let's actually be precise. Let's say we have X of U, and this is a subset of R dim M. So if you consider the composition of these 2 maps, which is the map X after gamma, this would be the representation of the map gamma in terms of a chart. Right, so I have a curve going through the room. It's a very abstract manifold still, but then I look at my room in terms of a chart, and now this map X after gamma, well, it's just a function that goes from R to R to the dim M. And we can definitely describe continuity using real numbers in Euclidean space quite well. And we could try to define the continuity of this curve gamma here using this chart representation. So what we could try to do here is we try to define continuity in the following way. We say gamma is continuous if the chart's representation, which is X after gamma, is also continuous. Right, so essentially what we're doing here, we have the curve going through the room in an abstracted manifold, and from my perspective, I set up my chart in some specific way, and if I see that the curve is continuous, then I define this map gamma here to be continuous as well. Now the question is this a good way to define it? Because you might have another person standing in the other corner of the room, they're looking at the exact same curve through the manifold in the abstract manifold. Can we be sure that they also see a continuous curve? So what this looks like in terms of this diagram here is this is my perspective over here. We can take a look at someone else's perspective. So this would be using the map Y, let's say, and we're just going to assume that the chart domain is the same, just to keep things simple. So this would be Y of U now, and what they see is Y after gamma. This is their representation of the curve through the room in terms of their chart, in terms of what they see. And the question is, can we be sure that Y after gamma is continuous as well? And well, the idea to check this is to, well, how can we represent y after gamma in terms of x after gamma, in terms of what we see? Well, the trick is to consider the chart transition map up over here, because going from R into Y of U here, going in on this arrow, is really the same thing as going down here and then up to Y of U. So we have to do the following check here, if you want. You notice that y after gamma is really the same thing. Well, we do, what is it? This chart transition map first. What is this chart transition map? It's y after x inverse. So this is y after x and then inverse. And then this is composed with x after gamma. So you do the composition with x after gamma here. And now let's suppose that x after gamma, our perspective of the curve, let's say we see this guy as being continuous. So this is continuous here, okay. Can we be sure that the other person's perspective is also continuous? Well, yes, it turns out to be the case because of y after x inverse. This is our chart transition map over here. This guy, chart transition maps are always continuous. So this guy, this is continuous. And because now we have the composition of continuous maps, y after gamma is also going to be continuous. And the key really is here that these chart transition maps, these are always going to be continuous. So if what we see is not continuous, then it can't be that this guy here is continuous. And yeah, if we see it's continuous and the other person also sees it's continuous. So you can see because we picked this other chart here, it's really any arbitrary chart. This is a good way to define the continuity of a curve, a gamma going through the room, because it doesn't matter if we select my perspective to view the curve or the other person's perspective to view the curve. We see continuity anyways. It doesn't matter which perspective we take. So we can say that the map gamma is continuous if from one of our perspectives over here we see a continuous curve in the chart representation. Right? And it turns out that gamma is indeed its continuous map anyways, because X is a chart map, it's a homeomorphism, and if we see a continuous map because we have a homeomorphism here, it must be that this gamma here is also continuous. Right, so it might seem a bit silly to define continuity in terms of charts because we already know what continuity means because these guys here are topological spaces, but this is the setup type of thinking that we'll need in order to define differentiability, which is what we'll do right now. So let's consider the exact same case now, but with, instead of continuity, we're going to take a look at differentiability. So let's take the exact same setup we have before. Let's say we have a curve, R into some subset U, which is, subset of M. And then we have a curve gamma here. Now what we want to ask is, well, is this curve gamma, is this guy differentiable now? And well, first of all, there's many classes of differentiability. You could have C1, C2, or C infinity. But let's just say differentiable as a general term for now. So we want to define differentiability of this curve somehow. Now, if we're just provided with this curve, it's actually impossible to determine whether or not this curve is differentiable. It's because we're mapping into a manifold over here, and in order to define differentiability, well, in order to determine if it's differentiable, you have to be able to write down some kind of difference quotient, which means you have to be able to subtract points and take the quotients of points in your manifold. You can't even do that yet because this is still a very, very abstract space. You can't subtract things, you can't divide things, you can't even write down a difference quotient. So if you just have this right over here, you can't even say if this guy is differentiable or not. But what we can do instead is we'll take a look at this curve gamma under a chart because we can represent this part of the manifold in terms of Euclidean space, which we know quite well, and we can differentiate in Euclidean space. So let's consider a chart map X that goes down, and this is X of U, once again, a subset of R to the dim M. And once again, we consider this guy here, so this is X after gamma, and then just like before with the continuity, we can try to define this curve to be differentiable if this map X after gamma is differentiable, because we know exactly what differentiability means if we have a map from R to the dim M. So we try to define gamma is differentiable if X after gamma is differentiable. Right, so what does this really mean here? It means if we have a curve going through the room once again, and now I look at my curve using my chart, my perspective, and if I see that the curve is differentiable, then I'm going to call the curve differentiable. So this is what we try to define so far. But the question is now, is this well defined? Because you could have another person, again, standing in the other corner of the room, and they look at the exact same curve, and are they still going to see a differentiable curve? Well, we don't know yet. So let's try to see what's going to happen if we have another person standing in the other corner of the room. So we have y, and then this would be y of u now, and this would be their perspective of the curve, y after gamma. So we want to determine if y after gamma, their perspective of the curve, if they see differentiability. Okay, so let's try this once again. So we do the check. So what we're going to check is that y after gamma. Well, just like before, we can write this as y after x inverse, and then compose with x after gamma. And y after x inverse, that's exactly this chart transition map over here, y after x inverse. Well, let's say we see a differentiable curve, so we see differentiability here. So this is differentiable. Can we be certain that y after gamma is differentiable? Well, the answer is no, because chart transition maps, if we're just given some arbitrary manifold, the chart transition maps are automatically just C0, and that's all. So these guys over here, these are just C0 or continuous. So you cannot be certain that someone else's perspective of the curve is also differentiable like what we saw. So this is going to be just at most a C0 over here. And this is a big problem if you try to define differentiability in terms of a chart. Because from what I see differentiability, but someone else might see some pointy curve or something like that. That's no good. So what's the fix to this? What is the fix? The fix is to make sure that the chart transition maps aren't differentiable, because if you have differentiable and then differentiable, well, this guy over here is also differentiable as well. So the fix that we want is that the transition maps must be differentiable. Right, but we've kind of already seen this in the previous video when we took a look at atlases. If we have chart transition maps which are differentiable, and when I say differentiable, you do have to talk about a specific differentiability class like CK or something like that. It just means that we have to equip our manifold with a CK atlas. So the idea is now we have a manifold and we're going to put only a CK, or actually I should have written maximal CK atlas onto our manifold. And what that allows us to do, if we have maximal CK atlas, that means these chart transition maps over here, they're going to be CK, which means the way we define differentiability of this curve gamma, which we couldn't do previously, it's going to be well defined. Which means it doesn't matter which chart I choose to look at the exact same curve gamma, we're all going to see a differentiable curve. And because no matter what perspective we use, we see a differentiable curve, we're going to call our curve up over here in the manifold level, we're going to call it differentiable, even though we actually can't differentiate the curve gamma, but we want to define the curve to be differentiable. And the only way to do that is by using charts. Right, and once we put a CK maximal atlas onto a manifold, we get what's known as a CK manifold. And we write that, well, first of all, we have M and then O here. So MO, so far, that's a topological manifold. M is the set, and this is the topology we have. Now, this is, so far, just a topological manifold. We don't have any of this differentiability stuff so far because, well, we don't even know what charts to pick in order to make everything nice and compatible and so on. So what we need to do is we need to prescribe an extra additional structure, and that's exactly this atlas over here. So if we give our manifold a CK atlas, this guy is what we call a CK manifold. And of course, we're just going to choose the maximal atlas by default every single time because we want access to all the different charts that we could pick. So this is a CK manifold because this atlas over here exactly tells us what types of charts we can have. If we have a CK atlas, that means the chart transition maps between all the charts, they're all going to be CK because the charts are all CK compatible, which means that these chart transition maps right over here, these guys, they're going to be CK. So if you take a look at our perspective of the curve, and our perspective of the curve is a CK, well, the composition of two CK maps is again going to be CK. So the other person standing in the other corner of the room though is also going to see a CK curve running through. And that's because this guy over here is always going to be CK. So if I see CK, then the other person sees CK. That's a bit funny to say. And if I don't see a CK curve, then the other person doesn't see a CK curve. And yet, because it doesn't matter how we view the curve, differentiability is well defined. So we call the curve up over here, differentiable or a CK curve. And now notice we have a CK atlas here. You might ask, well, how on earth do we even go about choosing a CK atlas? Well, the thing is you don't really want to choose a CK atlas or CK maximal atlas. It's going to be a massive set to choose. What you do is you just simply assume the existence of such a CK atlas. And if we make this assumption here, well, every time you pick a chart to work on in your manifold, you know that two charts are always going to be CK compatible. That's really all the atlas does there for us. It tells us that the charts are all CK compatible, which means we can define differentiability in this manner here using charts. Now we can work with CK manifolds, that's completely fine, but from this point forward, all we're going to be taking a look at is smooth manifolds. So next videos and so on, we're only going to be taking a look at smooth manifolds. So these are going to be M as the set, O the topology, and the atlas. So this guy over here, this is going to be a smooth, and you don't have to write maximal all the time, you can just say a smooth atlas. And if you have a manifold equipped with a smooth atlas, this is called a smooth manifold. And a smooth manifold is what we're going to be using in basically every single video moving forwards. We're not going to be worrying about CK manifolds or anything like that. Now, sometimes it might be a bit cumbersome to write out MOA with a bracket. Usually what we do is we suppress this notation and we simply say something like M is a smooth manifold. So M is just the sets over here, but if we say it's a smooth manifold, then it really comes with the topology, which tells us what the open sets are, and the atlas, which tells us what types of charts we have. But really, because we're always going to assume the existence of some topology and some atlas that's going to work for us, we're not going to bother writing those all the time. We suppress it in the notation, so we're just going to say M as the set. And these two guys should still be in the back of your mind somewhere. It's not gone yet, because without them, M wouldn't even be a smooth manifold. It would just be a set. All right, so let's take a look at a quick application, I guess, of what we've done so far. So we've taken a look at these curves here. We know how to define them in terms of charts to be differentiable. Let's take a look at these maps between manifolds. Let's see if we can make sense of differentiability of maps between manifolds. So let's consider a map, I'll call it phi, that takes us from M to N, where these two guys, these are going to be smooth manifolds. So remember, if we have smooth manifolds, we can suppress the topology and the atlas, and we can just refer to the set as the name. Now we can take a look at what it means for this map phi here to be differentiable. And remember, we can't exactly differentiate this map phi here because we're working over manifolds. We can't take difference quotients or anything. So we have to work in terms of charts now. So let's see how we might want to do that. So we have manifold M and then manifold N. Now we want to take a look at charts, so we can only do subsets here. So we have, let's say, some chart domain U here and then some chart domain V here. Then we have our map phi, which goes between them. Technically phi restricted to U, but whatever. And to determine the differentiability of this phi, we can go down to charts here. So we can go down via charts maps X and then Y into X of U, and then we have a Y of a V as well. Right, so X of U, Y of V, that would be what these manifolds here look like locally in our perspective. So we can take a look at this phi here in terms of the charts as being the map that goes between these two Euclidean spaces here. We know exactly what it means for a map between Euclidean spaces to be smooth. So what exactly is this map? Well, we have to go, Y is the last one, so we have Y, then we composed with phi, so Y after phi, and then we compose with the X inverse because we want to go up, across, then down. So X inverse like so. So what we can define, we define phi is smooth if Y after phi after X inverse is also smooth. Now, technically, if you want to make sure phi is smooth, you have to make sure that this map over here is smooth along the whole entire domain of phi, because this is just checking on the small region. So you'd have to make charts along the path of phi if you can't cover the whole entire thing with one chart. But at least on this local region U here, you can define the smoothness of phi based on this chart representation. Now, you have to make sure that this is our perspective down over here. You have to make sure that someone else's perspective, they also see a smooth map phi as well. So let's choose another perspective. Let's say we're looking at the same chart domain U and V respectively, and we do this without loss of generality, otherwise the picture will get quite messy. So let's consider chart maps X twiddle and Y twiddle as well. So this might be someone else's perspective on these two manifolds here, and what they see is X twiddle of U and then Y twiddle of V as well. And then their map they would consider is this one over here, which would be Y twiddle after phi after X twiddle inverse. And the question is, is what they see, is that also smooth as well? Well, the answer is yes, because we're working over smooth manifolds here. So what you want to check is someone else's perspective, so you want to include your perspective in there somehow. So what you can do, you start over here, you go down here via, this would be the chart transition map X after X twiddle inverse. So X after X twiddle inverse, you go along your perspective, and then you go back up to where you want to end, and that would be Y twiddle after Y inverse. So if you write this guy out in full, it will be quite long. So the one you want to check is Y twiddle after phi after X inverse, or X twiddle inverse. Now this is equal to, now what you know that these chart transition maps, they're always going to be smooth because we selected smooth manifolds, which means they come with a smooth atlas. So all the chart transition maps are smooth. So you always know that these guys over here are always going to be smooth, or C infinity. These guys are always C infinity, which means that, this is our perspective over here. This is our perspective. If we see a C infinity map, that means that someone else's perspective over here, they will also see a C infinity map. If we don't see a C infinity map, someone else's doesn't see a C infinity map as well. So it is indeed well defined in terms of charts here, which is exactly what we want. So this is exactly why we need maximal atlases, so we know that the chart transition maps are, C infinity. Right, so still on this example over here, we have a map phi between two manifolds. We have some extra terminology, which I don't know if we'll use this again and maybe, but I might as well introduce it now. If phi is bijective, and it's also smooth both ways, so we know what smooth in one direction means, because we just check in terms of chart of going to the right is smooth. We want it to be smooth both ways, which means if you consider the inverse going back the other way, that means in these chart representations you want arrows going back the other way as well. If it's smooth both ways, then phi, this is what we call a diffeomorphism, or I'll just write diffeo for short. So a diffeomorphism, it's kind of like the upgraded version of a homeomorphism. So I kind of introduced this in the first video, I think. We said that we had a sphere over here, and this would be, homeomorphic to some kinds of potato shape, but this would also be homeomorphic to if we make a little crease in the sphere somewhat. So these would all be homeomorphisms. Right, the homeomorphisms, because if you consider a map phi that goes from one space to another, it's going to be bijective and it's continuous both ways. You're not tearing things apart or anything, and topology doesn't know what smoothness means, which means it doesn't know that this crease here even exists. But now that we have differentiability, we can define diffeomorphisms. Now this guy over here, this would be a diffeo, because if you have these two spaces, you have their respective atlases and whatnot, you can find a bijective map, which is a diffeomorphism using what we discussed over here. But over here, between the potato shape and the sphere with the crease here, this would not be a diffeomorphism, because diffeomorphisms now see this little crease you put in. And just to finish off for today, we're going to introduce one last thing, which is going to be used in the next video. This is going to be a special type of infinite dimensional vector space. So the infinite dimensional vector space, and this is a special vector space which gets the name C infinity and then bracket M over here. So what exactly is this set C infinity M? Let's just forget about the infinite dimensional vector space first. This is a set. It's defined to be the set of all smooth functions on a manifold M. So it's a set of all functions that take you from your manifold into the real numbers in some way, such that f is smooth. And now we're saying a function is smooth here, which means that M over here, these are going to be smooth manifolds, of course. We're always going to be considering smooth manifolds. So because it's smooth, it comes equipped with a special smooth maximal atlas over here. So yeah, we know exactly what it means for a function in the set to be smooth because we just check in terms of a chart. But what you do might already have an idea. You have your M, and then you consider a chart representation into your R to the dim M. Technically U here, but yeah, whatever. And then you have a function f, which takes you into the real numbers. And then you consider the chart representation of this function f, which is exactly f after x inverse. So you call a function f smooth if a chart representation under any chart, it doesn't matter what charts because we have a smooth manifold here, if this chart representation is also smooth. And you collect all of these guys together into one big set, all these smooth functions, and then this constitutes the set C infinity M, which will make an appearance in the next video. Now this is also a vector space. Probably won't bore you guys with the vector space stuff. You can trust me that it is indeed a infinite dimensional vector space. But yeah, how do you define addition and scale multiplication? You can add two functions together and scale them pointwise, so f plus g. So how do you add two functions together? Well, you can take a look at the action on a point on the manifold, and you just simply define this to be f of p and then plus g of phi. And then you can do the same thing with scale multiplication if you have a lambda, and then you scale multiply into f here. But what exactly is this guy? Well, you define it pointwise once again by setting it to be lambda times the function at the point p. And yeah, I should have added this is over the real numbers here. So these lambdas, these are real numbers. It's an infinite dimensional vector space over R, so you can add functions together, you can scale multiply functions. These functions are smooth, and we know exactly what smooth means because we have a smooth manifold, which means it comes with a smooth atlas and all the chart transition maps are smooth. So this was quite a long video. I've been recording this for quite a while. I don't even know how long it's been. But yeah, hopefully this gives you an idea of how we go about differentiating things on manifolds, even though we can't really differentiate the maps themselves because you can't write different quotients on manifolds. But yeah, we need differentiability because in the next video, we're taking a look at tangent spaces, which is we're going to go to a point on the manifold. We're going to roughly consider what are the tangent vectors there, and we need this concept of differentiability in order to do that. So yeah, hopefully you guys enjoyed this video. And until the next one, hope you guys have a wonderful day, and I'll see everyone later. Bye-bye.